Now, size really does matter. Also, it's getting a bit confusing talking about these different numbers, because we need to make sure that we specify whether we're talking about a number as a binary number, which is base 2, or a decimal number, which is base 10. To differentiate between the two, so we don't get mixed up, if we're doing a base 2 number, we write a little 2 in subscript next to the number. This isn't a power. It's not above the number, making it 11 squared. This is a subscript number, a little number underneath. And that tells me that that's 1 to the base 2. It's not 11. And 1 to the base 2 is a twoser and a unit, which equals 3, and I put to the base 10. I put 10 as a little subscript here, so that I don't get these numbers mixed up, because 1 to the base 2 and 11 are completely different numbers, and it'd be easy to mix them up. So using this subscript method, 8 bits is 11111111 to the base 2, which equals 255 to the base 10. So what would be the biggest number that we can store in 16 bits? Now, if you remember, the easy way of doing this would be 2 to the power of 16 minus 1. Okay, let's just check that. 2. To the power of 16 minus 1. Okay. So yes, that does it right. It is 65535. Now, when we're dealing with computers, there are some magic numbers. And one of the magic numbers that you must remember is 65535. It's a magic number that you will see again and again and again. So that's one of the magic numbers that we've come up with. Okay, even bigger one. 32 bits. 2 to the power of 32 minus 1. Haven't heard anything back from you yet. Is this because nobody knows, or because you're working on it? Yay! Big number, isn't it? Now, blasted, what's going on with this thing? Now, where we've seen these numbers before, just to let you know, there's one more little wrinkle in the story. And that's that when we talk about a K, if I say I've got 3742 volts, I could instead write that as 3.742 kV, kilovolts, where K means 1,000. One slight little wrinkle in the story is that when we're talking about computers, K does not equal 1,000. Instead, K equals 1024. And the reason why k equals 1024 is because that's 2 to the power of, oh blimey, I don't know what it is, 8, oh, I'll tell you what. Yes, you're right. So, in computing terms, 1024 is a K. So, what that means is that 65535 equals 64K. And that big number, 4294967, equals 4 gig. So they seem like strange numbers, but they do keep popping up. Now, we really need to start thinking about converting. We quite often need to convert from decimal to binary. Now, converting from decimal to binary, unless you've got a computer or a calculator that does it, can be quite tricky and complicated. So instead of converting from decimal to binary, what we do instead is we use another numbering system, which is called hexadecimal. Hexadecimal is base 16. See, hexi means 6, decimal means 10. So hexadecimal means base 16. Now what we do is, instead of going directly from binary to decimal, or from decimal to binary, if you go via hexadecimal, you find it a lot easier. The reason why it's easier if you go via hexadecimal, I'll show you an example. Firstly, the way to do hexadecimal conversions is just to have this table. So just have this table, jot it down somewhere in your notes, and if you want to find the hexadecimal equivalent of, say, 10, you just look it up on the table and you find it's A. And the binary equivalent of A is 1010. If you want to find the hexadecimal equivalent of 4, you look it up on the table and it's 4. And the binary equivalent of that is 0100. Now we have to use letters because we're only allowed to use one digit in each position because we have a positional numbering system. So if we're going to have 16 characters around our number wheel, when we get above 9, we're going to have to use new characters. So we use the characters A, B, C, D, E, and F. Okay, let's do some examples. I'm going to go from decimal to binary. I'm going to take the number 209. It's a decimal number. And I'm going to convert that number into binary. Now in hexadecimal, the columns went up as, they didn't go up hundreds, tens and units, they went up 256s, 16s, and units. Because it's base 16, so each column is 16 times the size of the previous one. So 209, to convert 209 into binary, I first convert it into hexadecimal. So the first question I ask myself is how many times does that number, 209, divide by 256? And I find there are no 256s in 209. So then I ask myself, how many 16s are there in 209? And the answer I get is that there's 13 16s, remainder 1. You may remember doing remainders when you were at school. So I say, how many 16s are there in 209? And I get the answer, 13, remainder 1. So what I do is I look up 13 on the table, and I look up 1 in the table. And in the table, 13 is D. And, well, 1 is 1. So now, using the table, I can write down the hexadecimal equivalent. And 209 is D. D is a 13. D, 1. So now, D, to convert this into binary, what I do is I say, right, D is equivalent to 1101. And 1 is equivalent to 0001. And end up with this. 209 equals 209 in decimal is equivalent to D1 in hexadecimal, and the D is equivalent to 1101, and the 1 is equivalent to 0001. Is everybody happy with that? Everybody happy to go on? Okay, I'm going to do another one then. I'll do let me make myself a little bit of space. Nope. Okay. About 117, base 10. 107 in base 10. First question I ask myself, how many times did it divide by 256? And it's still less. It's less than 256. So it's going to divide by that no times. Next question I ask is, how many times does it divide by 16? So I'd go 117 divided by 16 equals, and it's 7 and a bit. So it's 7 base 10, and 7 times 10 equals, that's 112. So 7 remainder 5. So 117 divides by 16, 7 times, remainder 5. 7 16s are 112, and so it's 7, remainder 5. Now, from the table, I now look up 7. And 7 in decimal is equivalent to 7 in hexadecimal. So 7 in decimal equals 7 in hexadecimal. And looking up the 5, 5 in decimal is equivalent to 5 in hexadecimal. So the hexadecimal equivalent of 117 is 7 5. 7 5 hexadecimal. Now I look that up on the table. 7 is equivalent to, here's the 7 column. I'll just highlight the 7 is equivalent to 0, oh, that's wrong. I don't want to have that maybe. 0 1 1 1. 5 is equivalent to 0 1, 0, 1. And it's all in base 2. How's that? Now, what I'd just like to say to you is that I allow 4 hours for these lessons, and typically we finish in about 2. So we have got all the time in the world to do these. There is no need to hurry. So if you have any doubts, I can slow down and do some more. So I think I'll move on, because we're now going to do the decimal to binary. Okay, I've got, sorry, a binary to decimal. This time, I've got a binary number, 10101111, and it's binary. To convert that to decimal, I chop it into nibbles. Nibbles is 4 digits. So that bit, that's 1 nibble, and that bit is another nibble. So I chop it into 4 digits. And then I go and look it up on the table, and I look for 1010. And 1010 is here. 1010 is hexadecimal A. And then what I'm going to do is I'm going to look up 1111. And 1111 is here. 1111 is hexadecimal F. So I just go to the table and look these up, and I find that 1010 is A, and 1111 is F. Now what I've done here is I've just put on top here, I just put a little reminder that the first column is units, and the second column is sixteenths. It's hexadecimal, so the second column is worth 16. So what I've got is, I've got A lots of sixteenths, and I've got F lots of units. So once again, going to the table and looking up A, I find that A is worth 10 in decimal, and F is worth 15 in decimal. So A is worth 10, F is worth 15. So what I've got is I've got 10 lots of sixteenths and 15 lots of units. Units are oneses. So I've got 10 lots of 16 and 15 ones. 10 lots of 16 is 160, and 15 ones is 15. So I've got 160 plus 15, which is 175. How are we going with that one? Who wants me to do another one? I'll tell you what, I'm not sure what that means. Give me a smile if you want me to move on, and unsure face if you want me to do another one. Okay, done. I'll do another one. Okay. Let's do 1011 1000. Just picking a number at random. So, looking that up on the table then. 1011. I looked that up on the table. 1011. There it is. 1011 is that column. And it's worth B in hexadecimal. Oh, that's not what I wanted to do. Bear with me a second. So, 1011 is worth B in hexadecimal, looking at up on the table. Now, the next one is 1000. So I'll look that one up on the table. 1000, and it's here. 1000, and it's worth 8 in hexadecimal. So let me just write that in. 8. And this is a hexadecimal number. So I have B8. So I have B, lots of 16s, and 8, lots of units. Going back to the table, B is worth 11 in decimal, and 8 is worth 8 in decimal. So I have 11 16ths and 8 units. 11 16ths is 160, 171. 11 16ths is 171. And 8 times 1 is 8. 171 plus 8 must be 179. Okay, so what we do is we just use the table. We just look things up on the table. Most of the time, all that we're ever going to do is we're going to convert from binary into hexadecimal. Because most of the time, once we've got to hexadecimal, we don't bother taking it into decimal. Hexadecimal is good enough. You see, it's a lot easier. If I was to say I want you to remember a number, if I said I want you to remember 10111000, that's quite hard to remember. But if I said I want you to remember B8, that's easy to remember. So mostly we just deal in hexadecimal. Okay, now what I've got here is an exercise for you to do. And what I'm going to do is I'm going to give you 25 minutes to do this exercise.